Assalamualaikum and very good morning, class. The next topic for this class is root locus. First of all, let me introduce myself. I am Dr. Rubia Ahmad from Faculty of Technology and Informatics Razak, and I will be teaching you um, this course on this topic, root locus, starting from this week until the end of the semester for SMJE 3153 semester 1 2021-2022. Most of my lecture notes that I'm going to share with you, as well as the examples, are from the book which I co-authored, entitled here Introduction to Control Engineering, and the publisher is UTM Penerbit, UTM Press. We just have an announcement from Penerbit UTM Press that starting from 26 to 31st December 2021, there is a 30% discount for any book from UTM Press. And if you're interested, you can purchase my book or any of the book from UTM Press from the UTM Penerbit website or Shopee. Okay, let us start our lecture. First of all, let us recap on the previous note on control system. Okay, if you look at figure 4.8, this is a typical feedback control system where we have Y for the output of the system, U is the input, and G is the transfer function for the system that we are investigating, and HS is the transfer function of the feedback normally from the sensor that we attach to the system. So for this type of feedback control system, the transfer functions can be determined as output over input equal GS over 1 plus GHS. From this transfer function, the characteristic equation is defined as 1 plus GHS equal to 0, whereby the characteristic equation is by setting the denominator of the closed loop transfer function to 0. If you have this transfer function ys over us, it will be the numerator over denominator. For the characteristic equation, we are interested in the denominator part. Okay, the characteristic equations will give the poles of the system, which are the important quantity for understanding the performance of the system in many ways. And we're going to look more example on this concept while sketching the root locus later on. Okay, if you can recap the transfer function equation. In general, the transfer function for a closed loop system as defined output over input, which is actually numerator over denominator, where we can simplify in the form as shown in the equation above, where Bm s to the power m plus Bm minus 1 s to the power of m minus 1 plus triple dot plus B naught is for the numerator, s to the power of n plus a n minus 1 s to the power of n minus 1 plus triple dot plus a naught represent the denominator of the transfer functions. Or in other words, if we represent it in terms of poles and zeros, it is shown here. Okay, the first, the numerator s plus z1 if we have more than power of 1. Okay, so we can simplify in terms of poles and zeros. So the denominator is for poles and numerator is for zeros. Okay, again, if I have a transfer function or a feedback control system as shown in figure 4.8, now what I want you to do, can you give me the equation for the first one? What is the closed loop transfer function of the system? Number two, what is the open loop transfer function of the system? Number three, what is the characteristic equation of the system? And finally, what do the roots of the characteristic equation represents? Okay, based on the feedback control system shown in figure 4.8. And I'm going to give you about 5 minutes for you to try to determine what is the closed loop transfer function, what is the open loop transfer function, what is the characteristic equation, and some notes on the characteristic equation. Okay, class, let us look at the solutions. Okay, for the feedback control system shown in the figure, the closed loop transfer function is actually KGS over 1 plus KGS HS. Okay, so the transfer functions, I think we've learned it previously. So the transfer functions for this system is KGS over 1 plus KGHS. What about the open loop transfer function? For this case, the open loop transfer function is KGS HS. So the three are multiplied. Okay, once we have the closed loop transfer functions, it will be easier for us to determine the characteristic equation. For the case of this the system's transfer functions, the characteristic equations is the by equating the denominator of the transfer function equal to 0, which in this case is 1 plus KGHS equal to 0. And what does the roots of the characteristic equation represents? Okay, it will determine the behavior of the system that we're going to look upon more in the next topics, in the next section. Okay, now let us go to the new topic, which is the root locus. After completing the section, you should be able to first sketch the root locus diagram, and then second one, show mathematically how the location of the poles change as the design parameters is varied from 0 to infinity for a second order system. So most of the example will be on the second order system, and utilize the magnitude and angle criteria. Okay, so this is the second part, is the one that we mentioned earlier regarding the characteristic equations. We're going to look how the positions of the poles change if we change or if we varies the parameters for the k, the gain of k, of the system. Okay, to understand more of root locus concept, let us look at the example shown in figure 4.9, where we have our input system US, the output system is YS, and then we have a gain K here, and the transfer function for the system that we are investigating is GS equal 1 over S times S plus 2. So definitely this is a second order system. And in this case, in this example figure 4.9, our HS is equal to 1. Okay, now let us look how the roots of the characteristic equation for this system change as parameter k changes from 0 to infinity. Okay, in order to understand that, we have to determine the characteristic equation of the system and find the poles of the system. So I'll give you about 2 to 3 minutes. Please determine the closed loop transfer function of the system and the characteristic equation of the system. Okay, class, can we proceed? Okay, for this equation, for this system, the closed-loop transfer function will be kg, which is k times 1 over s times s plus 2 over 1 plus k 1 at k times 1 over s plus 2. And if we simplify the equations, we will get the transfer function of the system. The closed loop transfer function of the system will be k over s times s plus 2 plus k. Okay, so therefore our characteristic equation will be s plus times s plus 2 plus k. So therefore it will be s square plus 2s plus k equal 0. So when we equate this characteristic equation, the denominator equal to 0, this is called characteristic equation. We can determine the values of poles. Okay, remember I mentioned earlier the transfer function is actually output over input or poles over zeros, the roots of the zeros over the roots of the poles. Okay, so in this case, we're going to look at the values of poles. So based on the characteristic equation, the roots of the poles can be determined minus b plus minus square root b square minus 2 plus 2b c over 2a. Okay, so by using this formula, so we determine that s equal to minus 2 plus minus square root 4 minus 4k over 2. Okay, so now let us look what happened to the poles if we varies our k from 0 to infinity. Okay, so from 0 to a bigger value. So in this case, we're not going to look at the infinity. Okay, so in this example here as shown, we look what happened to the poles when we varies k from 0 to, let's say, 2. Okay, for the beginning, if k equal to 0, the starting point, okay, if you put k equal to 0 here, so it will be minus 2 plus minus square root of 4 over 2. So the poles will be 0 to negative 2. So let us mark here. So the first one is, so we're going to have two poles here because it is a second order system. So the poles are 0 and minus 2. Okay, so we have going to have 2 points here from k equal to 0, 0 and minus 2. Okay, now let us look what happened if k equal to 0.5. When k equal to 0.5, we put the value here and then we solve it. And then the poles are, the first one will be minus 0.29. Let's say it is somewhere here. And the second one will be minus 1.7. So let's say the red one here. Okay, so it will start from 0. For the green one, it will move to the left. And for the red one, we're going to move to the right. Okay, now let us look what happened if k equal to 1. And therefore, our poles will be both will have minus 1. So therefore, the green one from 0 to minus 0.29, and then it should go to minus 1. The same goes for the red one from minus 2 to minus 1.7, and then minus 1. And then what else? What happened next? When k equal to 2. When k equal to 2, we solve the equation here. The first one will be minus 1 plus j. So let's say I represent here minus 1. This is minus 1 for real axis. Let's say the imaginary, this one is plus j. Okay, and then another one for the red one, it will be minus 1 minus j. So if we increase the value of k from 0 to a higher value, we can see that the poles will move here from here to For the green one, it will go to here until it's made at the -1, and then it will go up, up, and up to infinity actually. And the same thing goes for the red one, from -2 to -1.7, and then -1, and then -1 minus j, and up until the minus infinity. So this is telling us what happened if we varies the value of k's. Because earlier you learn about the concept of stability in the S-plane. Okay, so in order for us to make sure that the system is stable, we have to choose a proper value of k, so that our system will lies in the stability region. So this is the concept that we're going to look at details later. Okay, so this is the conclusion that we can observation. The loci start at the open loop poles for k equal to 0. So when k equal to 0, the root locus will start at the open loop poles. Okay, earlier we determined that the open loop poles are 0 and -2. So this is the starting point. Okay, the loci start at open loop poles for k equal to 0 and terminates at the open loop k equal to infinity, and it will terminate in infinity at infinity. Okay, since we know that the general transfer functions of a closed loop uh, system is here given here, the open loop transfer functions is kghs, or in other words, because the GHS will have numerator and denominator. If we simplify it, it is actually K numerator over denominator. Then if we put it together, YS over US, or the output over the input, is actually KGS ds over ds plus K and S, where N and D are the numerator and denominator of open loop transfer function. Therefore, the closed loop poles are the roots of the characteristic equation 1 plus GHS equal to 0. Okay, and then from this observation earlier, if k equal to 0, the characteristic equation become denominator equal to 0. If k equal to infinity, the characteristic equations become numerator equal to 0. And another important theory on this root locus that we will apply later, okay, is the angle and magnitude criteria. Okay, section 4.3.2 on my textbook is discuss on this particular criteria, which is called angle and magnitude criteria. All poles must fulfill the angle and magnitude criteria based on the characteristic equation. What does it mean? So therefore, from this characteristic equation, we can say that KGHS must equal to -1. Okay, for this KGHS equal to -1, two conditions must be satisfied by every point of the root locus. Okay, applying this concept, the magnitude of KGHS equal to 1, and then if we apply that, we will have that argument of KGSHS, which actually argument of the numerator over denominator. In other words, 180 degrees times 1 plus 2k. The application will be discussed further in next topic of the root locus. Okay, to understand this concept of angle and magnitude criteria, let us look again another example. The open loop transfer function given here is that KGHS, this is called, if K times G times H, it is called open loop transfer function. If it is KG over 1 plus KGHS, then it is the closed loop transfer function. Okay, so for this open loop transfer functions, find the transfer function, closed loop transfer function find the values of poles from characteristic equation. Once we have the closed loop transfer functions, we can have the characteristic equation and then show the change in poles location when parameter k varies from 0 to infinity. This is the same as earlier. Okay, let us look how it is solved. Okay, so the closed loop transfer function will be kg over 1 plus kg hs. In this case, h equal to 0. So therefore, based on this equations, so the closed loop transfer function will be the numerator over the denominator plus the denominator. Okay, so the ks plus 1 plus kghs is actually the denominator plus the numerator. Okay, so by solving this, we get the characteristic equation, which is s squared plus 2 plus ks plus k. And then we can determine the values of poles, the roots, using the concept of this one. Okay, minus b plus minus square root b square minus 4ac. This the roots equations. Okay, so please try to solve that. Okay, so the values of poles is shown here. And then let us look what happened to the root locus when we varies k from 0 to infinity. Okay, if k equal to 0, okay, put k values 0 here, we can see that the poles are at 0 and minus 2. So let me put in the graph here. So there will be two root locus. The first one is when k equal to 0 at 0, k equal to 0 at minus 2. And then if we look what happened for if k equal to infinity, so the roots will be moving towards minus 1 because it is infinity, yeah? And then another one will be minus infinity. So the first one will be 2 minus 1 and the second one will be 2 negative infinity. So I differentiate here. The red one is the open loop poles and the green one is open loop zeros. Based on our closed loop transfer functions, okay, our open loop zeros is s plus 1 here equal to 0, so s is minus 1. Okay, so this is the open zeros. And then x is the open loop poles. So what can we conclude here is the root locus will end at open loop zeros as well as implied zeros at infinity. If we have a zeros, okay, so the poles will end to that zeros or it will end to infinity. Okay, so in this case we have two root locus, the first one here and the second one here. So if we have a pole, if we have a zeros, one of the root locus will end at the open loop zeros, while the other root locus will end at infinity. Okay, this is on angle and magnitude criteria. So let's say we have a third order system here, okay, which is k over s squared plus 4s times 6. Using angle and magnitude criteria, show that s1 equal to minus 1 plus j is one of the roots of the characteristic equation for the control system if k equal to 4. Okay, let us look what happened if k equal to 4. Okay, so first I solve what happened if k equal to 4, and then I will have these equations 4 over s squared plus 4s plus 6. Okay, and if you solve for roots, okay, so it will be this one if we let's say we put S1 or S1 as one of our roots, okay? So I put S minus 1 plus J to the equations. So this is my equation, the characteristic equation finally, if I solve it. So it will be 4 over minus 1 plus J times 2 plus 2J equal to negative 1. Okay, and then, okay, if S1 equal to minus 1 plus J is a root, okay, so it will be somewhere here, representing by the small box here. Okay, and then if you look at the open loop transfer function, which is s squared plus 4s plus 6, okay, so we going to have three poles. One is s equal to 0, another one will be minus 2 plus minus 1.4414J. Okay, the one will be positive and one will be negative. So the x point here are the poles. Okay, so when we see that S1 is one of the roots, okay, so we have to determine what is the angle from the roots to this S1. Okay, so we have three roots here, or three poles, and we need to determine the angle, okay, the angle of these poles to the point of S1. So let's say my first pole is 0, this one. So the angle was measured from 0 to the point here, so representing by the value of theta 1. And then the theta 2 here, the second pole P2 is minus 2 and minus 1.414J here. And then let us determine the angle, which is represented by theta 2, and the degree is 67.47, whether you can measure using the compass or by looking at the graph. And another one is theta 3, since it is in the negative region, so the theta is minus 22.49. And then when we sum this all these three values, it is my 180. So it fulfill the first requirement, which is summation of theta, summation of KGHS should be 180. And then the second one is the magnitude condition, which is the magnitude of KGS should be 1. And how do we measure the magnitude of the KGH? Will be the dimension of from poles to the roots. So this one is D1, D2, and D3. Then by putting all this value to this equation, yes, we have the value of of 1. Therefore, the two requirement is satisfied. Okay, so this is the first concept of root locus, and we will learn more about the examples and how to sketch the root locus of a feedback control system in the next class. Thank you.